It's Alana Taki, and I'm back to share with you more chapter lecture notes. I know it's exciting. We're moving into chapter 4. Now, chapter 4 is the chapter that we are going to talk about bivariate data. I say we, but really it's me going to talk and you're going to listen. Sorry about that. All right, so we're going to start off with scatter diagrams. So scatter diagrams look a little like, hold on, that. There you go. So you have a plot and you have a whole bunch of dots. Right. This is every few years, the folks at MSU, Michigan State University, give a test called the TIMSS Math Achievement Test to 8th grade math students around the world. The following shows the results of the test for 43 countries. So there you go. So you can see, like, for example, we have some country that's got about 50,000. It's right here, 50,000 for its GDP. And it looks like the math scores are around, well, I don't know, 475 or so. And then you have a whole bunch of other countries. All right. So then, let me scroll down here. We have the response variable is the variable whose value can be explained by the value of the explanatory or predictor variable. All right, well, that definition's a little fuzzy, but let me just say that in general, the response variable is the one that automatically changes because of a change in the other variable. Let me put it this way. The response variable is the one that depends on the explanatory variable. I know a lot of people don't like the words independent and dependent because that implies a certain causation, and that's not what I'm trying to say, but it's the one that we pick to be the one that's responding, so that if explanatory changes, then the response is going to change too, but because the explanatory changes. In other words, explanatory is like your X if you were in algebra class, and response is like your Y if you were in algebra class. All right. So what is the explanatory variable in our case? Well, again, explanatory variable is like your X, so that's going to be income per person, and that's GDP per capita, right? And the response variable is their scores on this test. Math test. Cool. Now, the oil-rich country of Qatar is the, I don't know if I'm pronouncing that right, but is the wealthiest nation in the world with a GDP of $76,900.53 per person per year. But it only scored 307 on the math test. Let's circle Qatar and what might be a problem with including Qatar in this data set. All right, there we go. I managed to get a circle around it. So Qatar is over here. So if Qatar is in there, what might be a problem with including Qatar in this data set? As you can see, Qatar is very far removed from the rest of the data. Data points. It has a very high income per person, but a low test scores, or average test scores, but low average test scores. Why would that be? Well, Qatar is a country rich with oil. But historically has not had a public education system, say, or a strong public education background, or something like that. How about that? Has not had public education. I don't know that much about Qatar, but the other point of the matter is that it's an outlier. It's a very far removed outlier from the rest of the group. So it could be problematic to include it because there's probably something going on in that country that makes it so much different than the rest of the group. And, unless you're, the ambassador to the region, you're not really going to know all the things that are going on. All right, so what does this lovely graph up here reveal about math scores in the world? Well, not surprisingly, generally speaking, with the exception of Qatar, right? Generally speaking, the wealthier a nation is, the better it's 8th graders do on the Tim's math test, right? I mean, if you disregard this guy down here at the bottom corner, just look at what's left. The higher the countries, the higher their math scores tend to be. The lower the country is in income, the lower their math scores tend to be. It's not perfect, of course. You can have some low-income countries doing very well, right? And some high-income countries not doing so well. That happens. But in general, you see a trend. Alrighty. Now, what you've just seen with that scatter plot is relationships. And we're talking about bivariate data here. This is the only chapter really that we talk about bivariate data. We have one variable, an x variable, and then we have another variable, y variable, and they're working together. So you have your income and you have your test scores, right? That's called a direct relationship or a positive relationship, right? When one went up, the other went up. When income went up, test scores went up, okay? By the same token, let's say as exercise goes up, weight goes down, right? So you put exercise down here on this little guy, right? And then weight over here on the y-axis. That would be a negative relationship because the more you do one, the lower the other one is. All right, then you can have nonlinear correlations. These have very strong relationships, but they're not linear. There's the quadratic relationship, makes kind of a parabola shape. It can be upside down too, right? Face has kind of U-shaped. You can have an exponential. Exponentials are really big and really big deal in like biology, finance. A lot of those things follow exponential curves. Or you can have it so that there's just no relation at all, like I don't know, height and IQ, right? Short people got no reason, right? So if you have height down here as your x variable, IQ over here as your y variable. For adults, it makes no sense because your height has no bearing on how intelligent you are. So please be careful and notice that the bottom one means there's no relation. These two in the middle, there's a relation. It just isn't linear. And linears are the ones that we're going to be working with the most. Linear patterns are what we care about. To be honest with you, exponentials are kind of a big deal too, but we're not going to work with them very much. Actually, we're not going to work with them hardly at all. All right, so let's look at that exponential data just a little bit more. This is from the lovely website gapminder.org, which I absolutely adore, and we'll be working with a couple other times in the course. So gapminder.org has this site, or has this data available, and this is the income per person down here, and this is the life expectancy. And you can see this is for, and you wouldn't believe how many students miss this, this is for the year 2009, right? See the big 2009 in the background? So for example, in 2009, this country over here has an average income of 15,000 and a life expectancy of about 50, right? There's a country over here that's about 75,000, probably Qatar to be honest, and a life expectancy of 76. Right, and then all these other countries. And can you see the arc? See how there's an arch to it, right? It's exponential. And if you look on the sides, it says lin and lin. That means those were linear, right? So this appears to be, whoopsie, hold on, I went too far. All right, it appears to be depicting an exponential graph, right, relationship. It's an increasing one at that, right? Increasing, right? The more income in a country, I know this is going to shock you, but the more income in a country, the higher the life expectancy. I know, shocking. Revelations all over the place today. All right, so there we go. So that's the kind of relationship you're seeing in that. But it's an exponential one. It's not direct. It's more arched. And you can see that a lot of these countries are packed in down here. We'll talk about that right here. Because believe it or not, this is the exact same graph. These are the same dots. These are the same countries. See that dot over there on the far right? That is this dot right here, right? So what happened? What changed? We'll take a look at it. Life expectancy, 20, 25, 30, that's all the same. But what's different is down here. You see this? If you look at your bottom axis on the one above, it goes 10,000, 20,000, 30,000, and so on. But the problem with that is roughly, half the countries in the world are under 15,000. Look, they're all packed in down here. See them crammed in? So especially this line right here, look at that. There's a whole bunch of countries that are extremely poor, and you can't get at the differences between them because they're all jammed in like cordwood. All right. If you go down here, look at the scale. 400, that's 800. Then you get 1,000, 2,000, 4,000, 10,000, 20,000. I'm multiplying. Look. 1,000 times 2 is 2,000. 2,000 times 2 is 4,000. 4,000 times 2 is 8,000. That would be in here. And then they hop to 10,000 because it's convenient, 20,000, and so on. And you see over here it says log, right? That's because this one uses a logarithmic scale, right? The scale on the horizontal axis has been changed from linear, L-I-N, right? Linear. Linear means it goes up by the same amount every time. 10,000, 20,000, 30,000, etc. To logarithmic, meaning we multiply. Instead of adding 10,000, we multiply by 2, right? 1,000 times 2, 2,000 times 2, 4,000 times 2, that's this mark in here. Then they were like, okay, well, we don't want to go 16,000, so let's start again. 10,000, 10,000 times 2, 10,000, right? And so on. All right, that's called a logarithmic scale. It's the only thing we're going to do with logarithms, to be honest. A logarithmic scale, instead of adding the same amount every time, multiplies by the same amount every time. Now, why would that be useful? Well, a logarithmic scale is really useful if your data is got a large range of values, or if it's tightly packed, right? So if you get things so crammed in there, like this one, that you can't really see what's going on, try a logarithmic scale and maybe you'll be able to get a better view of those poor countries, right? Because literally, look, there's 15,000 right there. Look at that space on that graph. Whereas 15,000 on this graph is here. So everything's packed in down there and you can't really get at the distinctions between the countries. All right, so we're only going to be looking at log scales. You're not going to have to compute them or anything. They are highly useful for science, especially. pH, your acid-base thing, decibels, Richter scale, those are all logarithmic scales. So they come in handy in science class. All right, so down here, I've got two graphs side by side. One of them is linear, and one of them is linear logarithmic. Your mission is to figure out which one is which. So, U.S. spends more on healthcare. Circle the U.S. So let me insert a... All right, hold on, let me pause you. There we go. So we've got infant mortality is on the y-axis, and then the x-axis is how much you spend on healthcare as a country as a percent of your GDP. The U.S. spends the most of any country in the world on healthcare. We are over here, where that circle right there. Okay, so label each graph's axes as log or linear, and which is the better graph. So let me pause you. I'm going to label. Hold on one sec. There we go. All right, so I've labeled these as linear and log. So you can tell these are linear because they're going up by the same amount every time. 2, 3, 4, 5, 25, 50, 75, 100, and so on. The only one that's different over here is the logarithmic scale here. 2 times 2 is 4, and then they go to 6. 10 times 2 is 20. 20 times 2 is 40, right? And so on. 100, 200, 400. And then I ask which is the better graph, and there's no question about it. Graph number 1, this one is the better graph. Because in the graph number 2, you got this big pile up down here, right? And rather than having that giant clump of everybody at the bottom with their infant mortality, it's not really helping you see the differences. If you spread it out with the logarithmic scale, you can really see the differences between the countries. Because they go from as low as 2 infant mortality rate, 2 per 1,000 births, all the way up to 200. Right? And you're able to spread that out and see it better with a logarithmic scale. There. And that's what I just wrote there. Right? The infant mortalities go from 2 to 100, so the logarithmic scale does a better job of spreading that out. All right, we're all done with this page. I'll meet you back here for the next one. See you then.